Multiple bodies. This is another extension of Newton's second law problems. So we're going to do the exact same things every time. We're going to do that exact same thing. So let's look. We've got a force pushing on a big box. In front of the big box is a little box. Okay, big M and little m. So I'm going to do two free body diagrams, one for the big M box, one for the little m box. And I'm going to pick that direction as the positive direction for motion. Okay. I'm really not even going to bother. I should have drawn a vertical positive coordinate axis, but that's not the one that's very interesting in this. Okay, so for the big box, capital MG is the weight. The force F is absolutely a contact force. It's pushing to the right. We also have the normal force from the surface. I said it's frictionless. If it weren't frictionless, the friction would be pointing to the left. But there's another surface, the surface of that little box M. That's pushing back. Okay, we know it's not pushing forward. It doesn't help move it. The fact that little m is there doesn't help make the big box move faster, right? So that is a force perpendicular to the surface of the little m box. And I'm going to call it F21, the force of the second box on the first box. It's a normal force. Okay. Now let's look at the second one. Little mg down, that's the field force. Let's go around that box. Well, there's a surface at the bottom. It's going to provide a normal force. Would provide friction if it were not frictionless. And then there's the surface of the big M box. So there's a normal force from that surface, perpendicular, pushing in that direction. I'll call it F12. Now, what we know from Newton's laws, from Newton's third law, is that F12 is equal and opposite to F21. So they have the same value. Now, I can look at that first one and I can say, well, I know that normal force is not accelerating up or down, so the normal force is mg. For the second box, I can do the same thing, little mg. And I can get to my Newton's laws. So in the x direction, for the first box, for the big M box, F in the positive direction minus F21 equals ma. For the little box, F12 equals ma. Now, one thing I like to do on this is I like to add these things. F21 and F12 have the same magnitude, right? So if I add the terms on the left, F minus F21 plus F12, and again, those are the same size. If one of them's 5 newtons, the other's 5 newtons. So think of it, F minus 5 newtons plus 5 newtons, that just ends up being equal to F. And then we add up the two on the other side, big MA plus little ma equals big M plus little m quantity times A. Then to get A, just divide by that total mass, and we get A equals F over M plus M. Okay, so we've solved that. That's not too bad. And then we can use that A in either of those two equations above, F minus F21 equals MA or F12 equals little ma. We can just substitute that in and we can find that, what we call an internal force, okay, the force of M on M, big M on little m or little m on big M. So if we do that, I'm just going to take that equation, F12 equals ma, and A is capital F over M plus M. So there is my final calculation of what that normal force is there. Now we know everything. We know the normal forces between the floor and the boxes, and we know that Newton's third law. So in the x direction, we've just figured out what that F12 is, but F21 is the exact same thing. We can simplify this. We can make this a little quicker. And the way we do that is treat that as a system. These two objects are traveling with the exact same acceleration, right? It's not like one is getting ahead of the other one. They're both traveling as a unit. So as they are traveling as a unit, we can just kind of put an imaginary box around them and treat them as one big thing. The total mass of that would be capital M plus little m. So when we do a free body diagram for the system, it looks like that. Big mg plus little mg is m plus m times g. Okay? Then we've got that F pushing to the side, no friction, so nothing in the other direction. And the normal force. And the normal force is going to be the same as the force of gravity because it's not accelerating up, not accelerating down. System. For the system, Newton's second law in the x direction, the force, F, equals m plus m, that's the mass of the system, times A. So Newton's second law, the total force horizontally is F. And I didn't draw my frame of reference, but it's the same frame of reference. In fact, I wouldn't be surprised if the slide pops it up in a second. So the acceleration ends up being capital F over m plus m. Force applied to that total mass. See how easy the acceleration is, much easier than it was in the previous problem. But I can't just walk away with that unless that's all they ask for. They may ask for what is the force of capital M on little m. And to do that, I still need the free body diagram and the Newton's second law for one of the objects. The easy one is that little m. And remember how we did that in the last one? F12 equals little m times A, and we plug in that A there. Pulleys very much like this, okay? We can do this with two Newton's second laws or really treat it as a system. So first I'm going to do the two Newton's second laws, the two free body diagrams. And this is a massless, frictionless pulley. This is important because when we get to rotation, we're going to have pulleys where you actually have to accelerate the pulley as well. Here we're assuming that string just slides freely over the pulley. And basically all the pulley does is redirect the tension, redirect the string. So if we look at this, whatever tension is pulling on capital M, that same tension is pulling up on little m. It's the same force. Won't be the case when we have a pulley with mass and friction on between the rope and the pulley. Okay, so we have to have a consistent frame of reference. It's a little weird. We have a curving frame of reference. In other words, if little m accelerates downward with acceleration A, big M will accelerate horizontally with acceleration A. And we have to make sure those two accelerations are consistent. We can't define big M's positive to the left and little m's down. They have to be consistent, same direction, even though we're considering this curved frame of reference. So for the big M, to the right, I'm going to consider positive. And again, I'm just going to worry about the direction of motion for the frame of reference on each of these, okay? So we have mg down, tension to the right, normal force up. If there were friction, there would be a frictional force to the left. Okay. For the second one, for little m, it's really simple. Little mg down and tension up. Okay. So that horizontal frame of reference arrow, it goes with the first free body diagram, and the vertical one goes with the second. We're not going to worry about in the capital M. We're not going to worry. I didn't bother drawing positive direction vertically for that one. Because it's such an easy Newton's first law application right there. In other words, mg equals the normal force. And that's because there are no other up and down forces. Okay? So we've got our two free body diagrams, and what we have to do is solve Newton's second laws in the direction of motion for each of them. Okay? Now I've got to point out, this is probably the most important thing on this slide. The tension is not equal to little mg. Why? Think about that for a second. And if mg was equal to tension, this thing wouldn't accelerate at all. It would be in equilibrium. So tension is not equal to mg. Do not do that. Always assume if it were at rest, if there were friction holding this still, it would be equal. But if it's accelerating, tension has to be less than mg, little mg. So for big M, in the direction of motion, sum of forces equals ma. I should write it, but it was going to get crowded. So tension, T, equals big M times A. For little m, mg minus T in the direction of motion is little m A. And again, what I like to do is I like to take those two equations, two unknowns. I could just substitute the first one into the second one. I like adding those. Mg minus T plus T, or T plus mg minus T equals mg. And then we add the things on the right. They have to be equal to that. Total on the left equals total on the right. Capital MA plus little ma is m plus little m A. then we solve for A. Okay? And to find the tension, I could use either one of those equations. And I used little m. Okay? And all I have to do is substitute in for A, mg over m plus m. And then I solve that for rearrange and solve for tension. It ends up being tension equals mg minus m times quantity little mg over big M plus little m. Just getting the tension alone in that equation. And again, those two tensions in the two free body diagrams are the same because it's a massless, frictionless pulley. It just redirects the force. We can also treat pulleys as a system. And we think of it as a funny system. It's a bending system. It's weird. So when we look at that free body diagram, it's really not a free body diagram when you treat it as a system, but we look at all the external forces. Capital MG pulls down on that part, and there's going to be a normal force up. Those are external forces, right? The Earth's gravitational field, or the mass of the Earth using universal gravitation, provides mg. The surface of that table pushes up with normal force. If there were friction, that would be an external force too. Okay? And then we go around this thing. Oh, the pulley, I really should have made that system smaller so the pulley's not included. It should just be the rope. But the pulley pushes up on the rope. If the pulley's part of this, we really can't consider the pulley part of the system in this. So it pushes up on the rope, and then little mg pulls down in that direction. Again, we've got our frame of reference being sort of to the right and down, right? Now, if we look at that, the two normal forces and capital MG are perpendicular to the direction of motion. So when we write a Newton's second law for the system, we have little mg is the only force, external force, that would make it accelerate in the direction of motion, right? So mg pulls it in that direction. If friction were there, we'd have mg minus the force of friction on that capital M. mg equals capital M plus little m times A. Because it's the important thing is the force on the system equals the mass of the system times A. So we have to include both m, little m, and big M, because that's the total thing that's getting accelerated. So really easy to solve for acceleration. Just rearrange that equation. We have little mg over big M plus m. Now again, there's no free lunch. To find the tension, we still have to do an internal force, a free body diagram for capital M or little m. Generally, you would tend to do it for capital M because there's just one force on it, tension. Now putting it all together, the hard stuff. Okay, when you put it all together, we could have an inclined plane and a pulley. And if we do free body diagrams for both of them, we kind of have to do that because we've got to break up mg. So we have mg, we have tension and normal, just like we always have. We have little mg and tension there. When we break those up, on the left we would have mg sine theta, capital MG sine theta, pulling backwards in the negative direction, right? So in other words, that's pulling capital M in the negative direction. Little mg is pulling down, so that's making the thing accelerate in the direction of the frame of reference that we talked about. So little mg in the positive direction plus negative capital MG sine theta. If there were friction, there'd be another term in there, equals the total mass of the system times A. Okay, so we really only needed those two free body diagrams so we could break up capital MG appropriately. And then we've got an acceleration. Little mg minus mg sine theta over mass plus mass. If we do the free body diagram for little m, we have mg minus tension equals mass times that acceleration that we just solved for. I'm not going to simplify that, but easy enough to get t alone.